Okay, let me begin my today's session. And yesterday I was discussing about correlation, which tells us about the association between two random variables, which constitute a bivariate distribution. And I told you that to calculate correlation between two random variables, we actually use the formula given by Carl Pearson. The formula is called Carl Pearson's correlation coefficient, or sometimes it is also called product moment correlation coefficient. My discussion on correlation is not yet complete. Today also I'm going to discuss further on correlation. But before that, one particular point which I need to clarify, and that which was not discussed yesterday. Why this correlation is called product moment correlation coefficient? That point I must clarify first of all. Let us try to read the definition which is given in definition 7, as you can see, of the book of John Freund. It says, it goes by the name product moments about the origin. And the definition goes like this: the rth and sth product moment about the origin of the random variable x and y, denoted by mu r comma s prime, is the expected value of the quantity capital X raised to the power r multiplied by capital Y raised to the power s, and it is symbolically represented as mu. In suffix we write r comma s, in superscript we write prime, so mu rs prime, which is expectation of this particular product of the random variables. What does it mean? It means that you can multiply the random variable x with itself r times, and with that product you are multiplying the random variable y, which multiplies with itself s times. And this expectation is given by the following formula. For discrete case, we use double summation over x and y, x to the power r, y to the power s, and the probability function, which is the joint probability function fxy. Both of these quantities r and s takes values from 0, 1 to up to infinity. And if capital X and Y are continuous, the same definition is calculated with respect to integration, and we integrate this term, we integrate this integrand from minus infinity to plus infinity for both x and y. This is the definition of product moment about origin. Now, let us go to the next page and let's see what is product moment about the mean, because in our case, this definition is actually very important and it is directly related to correlation. I'll tell you the relation between this particular definition and correlation after I define the quantity. Just like the product moment about the origin, the product moment about mean is defined in the following manner. The rth and sth product moment about the means of the random variables capital X and Y is denoted by mu rs. The prime symbol is not there. Mu rs prime is for product moment about the origin, and without prime, we call it product moment about the mean. Though you have to keep in mind that this is not the usual practice for every author. In some author's book, you will find that they are retaining this symbol for product moment about origin and prime for product moment about mean. They just reverse the order. But before you use this, you have to clarify which is what. Okay. So this quantity is the expected value of the power of this difference multiplied by the power of that difference. Previously, it was simply capital X to the power R and capital Y to the power S. And now it has become capital X minus mu X. There is a printing mistake, as you can see in the book. So remember, this should be X minus mu suffix X to the power R, not mu X to the power R, and Y minus mu Y to the power S. Okay. So x minus mu x to the power r and y minus mu y to the power s, we consider its expectation. For product moment about origin, the mean value was simply 0. So you can consider that the product moment about the origin is a special case of product moment about the mean, because when mu x equal to 0 and mu y is equal to 0, then this becomes x minus 0 to the power r and y minus 0 to the power s, which is simply x to the power r and y to the power s. Okay, so this is the general case. Previous one is the special case. Anyways, so mu rs is actually expectation of x minus mu x to the power r multiplied by y minus mu y to the power s. We consider the double summation, and in case of the variables, in place of the variables, we write x minus mu x to the power r, y minus mu y to the power s, fxy, where r takes values from 0, 1 to up to infinity, s is the same, and for integration, we replace the summation by the integration. Regarding the PDF file of this particular book that I'm actually sharing with you, remember this thing, that the hard copy of the book which we have in our college is the old version and is considered to be the best one. This version which I'm sharing with you right now, it is a new version from Pearson, India. And in this version, if you are reading this version, you have to be very careful about some parts where some mistakes have crept in. Okay, some mistakes are there, notational mistakes, some spelling mistakes are there. So you just be careful while reading this out. As for example, if someone is not careful enough and he reads this particular part as mu multiplied by capital X, then he will be in trouble because it doesn't have any meaning. So capital X comes in the suffix. Remember this. Now my point is why this particular thing is directly related to correlation. Let us try to recall the definition of correlation. The correlation coefficient between the two variables capital X and capital Y is given by the quantity covariance of xy by sigma x into sigma y. Okay, and what is the definition of covariance? In terms of expectation, covariance can be written as e of x minus ex by multiplied by y minus ey. Okay, in place of ex, you can write e of x minus mu x, and in place of y, you can write ey, you can write y minus mu y. Okay, so in this case, you see that this quantity which is there is actually the special case of that. Just carefully observe this. Here, the only difference is that in place of r, we have considered 1, and in place of s, we have considered 1. Okay, so here r is equal to 1 and s is equal to 1. So this becomes the special case of that quantity. So covariance is actually a special case of the product moment. Covariance is a special case of product moment, and therefore the correlation coefficient where covariance is involved is called product moment correlation coefficient. That is the reason why it is called product moment correlation coefficient. I hope you have understood this particular point. Let us get back to our original note which I was sharing with you yesterday. Okay, so if you are not writing this, just take a screenshot quickly, because I'm going to move on to my correlation note now. Okay, yesterday, before the session ended, I was at this particular point, that the correlation coefficient between the two variables lie between -1 and +1. And you have already come to know of the fact that when the correlation coefficient is +1, then we say that the variables are perfectly positively correlated, and when it is -1, it is perfectly negative correlated. But in general, they lie between -1 and +1. So we are going to prove this result right now. Okay. To start with, we consider two random variables, capital X and capital Y, and we assume the fact that expectation of the random variable X is equal to mu X and expectation of the random variable Y is equal to mu Y. These are our usual notations. Okay. And also, you know that the expectation of the random variable E of X equal to mu X, that means if you consider this to be the sample values, then you can say that the average of the sample values is equal to the population average, whatever. Okay. Now, there is a trick. There is a mathematical trick which you have to well aware of. The trick says that you have to start with this particular point. This is the point where by which you can start your calculation. We know that expectation of this quantity, you can consider, suppose for the time being, I'm considering x minus mu x by sigma x as x prime. X prime is my quantity x minus mu x by sigma x, and y prime is the quantity which is y minus mu y by sigma y. So actually this thing is saying that expectation of x prime plus y prime whole square is greater than or equal to 0, and which is obvious because x prime plus y prime whole square is a positive quantity, so its average will also be a positive quantity. As at best, what can happen when we consider expectation of x prime minus y prime, if x prime and y prime are same, they may become 0. So together we have written this as plus minus. We have written between these two quantities, we have put the sign plus minus. Okay. So it is always a non-negative quantity, which is pretty obvious. Also, one thing I must clarify is that don't think that this x minus mu x by sigma x is the normal variate. It's the standard normal variate. It is not. Whenever we write a variable as x minus mu x by sigma x, then such a variable x prime is actually called the standardized variable. It is called the standardized variable. Now, if x prime is normal variable, if x prime is normal variable, sorry, not x prime, if x is normal variable, then x prime is standard normal variable. Otherwise not. Otherwise not. Okay. If capital X is normal variable, then x prime is standard normal variable. But here I'm not considering the normal variable. I'm considering a general variable. And this expression is actually coming from the definition of standardization. So that is what I'm actually using over here. Okay. So, okay, we have understood this point. Now, once you write this, let us write it over here. If you write E of x prime plus minus y prime whole square, what does it mean? You can break the squares. Okay, either you can write as a plus b whole square, or you can get a minus b whole square. So if I do so, I will get x prime square plus y prime square plus minus 2x prime y prime. That is what I will get over here, get from here. Now you can resubstitute the values of x prime. You know that your x prime is x minus mu x by sigma x. So I'm writing it as one more thing. You know that from the property of the expectation of x plus minus y is actually expectation of x plus minus expectation of y. Now, using this property, I can write it as expectation of x prime square plus expectation of y prime square plus minus expectation of 2x prime y prime. And this can be written in turn as expectation of x prime square plus expectation of y prime square plus minus 2 is a constant quantity. It comes outside the expectation sign. We can write this. Now you can resubstitute the quantities x prime, the value of the x prime as follows. In place of x prime squared, you can write ex minus mu x by sigma x whole square. In place of y prime squared, you can write y minus mu y by sigma y whole square. And similarly here. Okay. Now the next step gives me that since sigma x 1 by sigma x is the constant quantity, it can come outside the expectation symbol. But before it comes outside the expectation symbol, since sigma x is getting squared over here, so actually the constant quantity is 1 by sigma x squared, it will come outside. And we'll simply get e of x minus mu x whole square by sigma x square. Similarly, from here, we'll get e of y minus mu y whole square by sigma y square. And similarly, from this quantity, 1 by sigma x will come outside, and from this quantity, 1 by sigma y will come outside. So ultimately, we'll get 2 multiplied by this term, where the numerator is getting divided by the quantity sigma x and sigma y, product of sigma x and sigma y. Now carefully look at this scenario. We know that e of x minus ex whole square is actually the definition of variance of x. And this variance of x is denoted by sigma x square. Similarly, expectation of y minus ey whole square is variance of y, and it is denoted by sigma y square. So in place of, and we know that ex is mu x and ey is mu y. So in place of the numerator, we can write sigma x square, and in place of this, we can write sigma y square. So we get sigma x square by sigma x square and sigma y square by sigma y square. Also, just now we have discussed that this is nothing but the covariance of xy by definition, because it is the special case of the product moment. And therefore, in the numerator, we are writing covariance of xy. In the denominator, we are writing sigma x, sigma y. So ultimately, we have got this, which is greater than or equal to 0. Now, sigma x square by sigma x square means 1. Sigma y square and by sigma y square gives you 1. And covariance of xy by sigma x, sigma y gives you rxy by definition of the correlation coefficient. So ultimately, we are getting 1 plus 1 plus minus 2 rxy, which is non-negative. You can take 2 common, and we get 1 plus minus rxy, 2 multiplied by 1 plus minus rxy greater than or equal to 0. Now, you can divide both sides by 2. So we get 1 plus minus rxy greater than or equal to 0. And this implies that 1 plus rxy greater than or equal to 0, and 1 minus rxy greater than or equal to 0. Another case, another situation may arise from here. The product of the two quantities are greater than or equal to, this sum is greater than or equal to 0 means what? I mean, yeah, here you have to write in this manner. Either this, since I'm considering both the plus and minus case together, therefore I am separating it. It is not a product actually, since I'm writing plus minus sign together. So 1 plus minus rxy greater than or equal to 0 means both of these are true. 1 plus rxy greater than or equal to 0, 1 minus rxy greater than or equal to 0. From this expression, we are getting rxy greater than or equal to minus 1. And from that expression, I'm getting rxy less than or equal to plus 1. If I combine these two items, we are ultimately getting minus 1 less than or equal to rxy less than or equal to 1. So which proves our desired result, that the correlation coefficient between the two variables is actually lying between plus 1 and minus 1. And this particular note has already been discussed. In this note, we have already seen in our previous class that when two variables, capital X and capital Y, they are having a perfect linear relationship between them, then the correlation is positive, obviously positive, but it is the value of the correlation coefficient is the maximum value, which is 1. And if they are having the perfect negative relation, linear relation, then their correlation is negative and it is exactly equal to -1. In case of no correlation, we write the value to be 0. That particular part has not been explained yet. And I told you that I'll be explaining the zero correlation part later on. Now, let us consider this particular example. I have actually set several examples over here. One of the example is this one, where you can see, carefully observe that, just a minute. Okay, now carefully observe that if I consider the variables like this, if I consider this variable, two variables, and their values are given as follows. As you can see that in this case of X, there are a jump of +1. And in case of Y, there is a jump of +1. And here also. And here, if I consider this expression 1 and 3, there is a jump of +2, as you can see. So actually, Y is related to X by the function Y equal to X plus 2, as you can see very well, isn't it? Now, if I plot this as a scatter diagram, you observe what is happening. If I try to draw a hypothetical straight line like this, then what we are seeing over here, that some of the points are lying on the straight line and some of the points are above the straight line and some are falling below the straight line. So this relation is actually not perfect, although we are getting very correlation coefficient to be very nearly equal to 1. But I am writing here exactly the correlation coefficient which I am getting after the calculation, which is coming out to be 0.9863. It is happening because the correlation in this particular figure, in the scatter plot, some of the values are not falling on the straight line. So this is the scenario over here. Let me show you another example. Okay. Another example which I have considered over here as follows. So in this example, just look at this example, what is happening. So here you see that the jump of X is +1, and the jump of here also is +1, here also +1, here also +1. Jump of the items from in case of Y prime is +1, here it is +1, here it is +1, and here it is +1. And here you see that for the value of 1, for X prime to be, in case when X prime takes the value 1, Y prime is 0. And in case of Y prime, it is actually 1. In case of X prime, it is 2. In case of this, it is 4. And in case of that, it is 5. So actually, the direction is like this. Just carefully observe, this is the direction. If you write the direction from Y to X, it is +1, +1 is increasing. And if you are giving the direction from X to Y, you can write it as -1, -1 decreasing. But you know that when this happens, then the correlation is positive. So if you draw a kind of straight line now on the scatter plot, you see that according to this particular example, all the points are now lying exactly on the straight line, hypothetical straight line you are drawing. And hence the correlation coefficient is coming out to be exactly equal to +1. But in the previous case, it is it was not +1, it was 0.9836, which is very nearly equal to 1. The correlation is, the correlation between the two variable was very significant, but not perfect. And that is the reason why that was not perfect, but it is perfect. Okay. Let's see another example. In the last example, which I am showing over here, is that you see the variables have been chosen in the following manner. And here, when we plot the scatter diagram, as you can see that, just a minute, here the values of X are actually increasing by +1. And here the values of Y are actually decreasing by -1. So you can say that when one variable is increasing and another variable is decreasing, if such a scenario is coming out, then the correlation which you observe is the negative correlation. When we draw the straight line, hypothetical straight line, we are getting a straight line where all the points are falling on the straight line, but the straight line is in decreasing direction and correlation is coming out to be -1. So we say that between X double prime and Y double prime, there is a perfect negative correlation. Okay. So this is the thing which has already been discussed yesterday by doing some sort of calculation with the help of Excel. Yesterday, one of the students, he told me, and I shared his observation with you regarding the Excel values, which actually I didn't know. So therefore I am very much thankful to the student who actually observed this particular case. Anyways, we actually did these things explicitly in yesterday's class, but what we didn't discuss yesterday is the following, that what is the case of the correlation coefficient becoming 0 between the two random variables. Now you carefully observe this particular theorem. This theorem is very important. The theorem, what is this theorem is saying? We are going to prove this theorem first of all. The theorem is saying that two independent variables are uncorrelated, but two uncorrelated variables may not be independent. Suppose I am considering two statements. One of the statements is that, suppose first of all, we are assuming that let there be two variables, capital X and capital Y. Let XY be two random variables, capital X and capital Y, and the statement P says that capital X and capital Y are independent. And statement Q is saying that capital X and capital Y are uncorrelated. So in the theorem, we are actually supposed to show that P implies Q, that when the two variables are independent, they are uncorrelated. This means when X and Y are independent, this implies Rxy is equal to 0. That we want to prove over here. Now, we know that when capital X and capital Y are independent, then it is a theorem which says that expectation of xy is becoming ex into ey. Otherwise, you cannot write it. When capital X and capital Y are independent, then only you can write this. Now we know that covariance of xy is represented by the following formula: E of x minus ex, y minus ey. And if I write it in a computational form, this covariance formula can also be written as E of xy minus E of x into E of y. Now, when the variables xy are independent, E of xy becomes ex into ey. So ultimately, we are getting ex ey minus ex ey, which is equal to 0. So for for variables like capital X and capital Y, which are independent, the covariance between them is equal to 0. If covariance between the two variables is 0, this implies that Rxy which is equal to covariance xy by sigma x into sigma y, that also becomes 0. So which proves that when the two variables are actually independent, then the correlation coefficient between them is 0. But you just take a screenshot of this particular thing. Otherwise, the proof is already written below. You can see the proof. You can find the proof in the note itself. Don't have to write anything. Now the question is the converse of the problem is true or not? That means what? That means if someone says that the two variables are uncorrelated, does it imply that the two variables are independent? This is the question. In the theorem, in the statement of the theorem, we are seeing that it is not actually true. Two uncorrelated variables may not imply that the variables are independent. We are going to find out one counter example by which this can be proved. Okay, so let's see what example we have found out over here. We have considered two variables, capital X and capital Y, and we are going to calculate the correlation between them. And for the calculation of correlation, we need to find out this particular terms, summation x, summation y, summation xy, summation x square, summation y square. All of these terms have been calculated from here. Why? Because you know that if you use the formula, the computational formula of the correlation, then it actually is equal to 1 by n summation xy minus x bar y bar by 1 by n summation x square minus x bar square under square root 1 by n summation y square minus y bar square under square root. So that is the formula. So to calculate the correlation coefficient, actually we need this term, then this term, then this term. These terms are actually needed. And x bar, for x bar we actually need summation x by summation x. For y bar we actually need summation y. So all these terms have been calculated from the table, and we have found that summation x is coming out to be 0. Summation xy is coming out to be 0. These are the two highlighted points. So since summation xy equal to 0 and summation x equal to 0, as summation x equal to 0, this implies that x bar is also equal to 0. And therefore, as summation xy is 0 and x bar equal to 0, therefore the numerator of this term is 0. Okay, and since this numerator is 0, rxy is 0. So we have got an example where we have found that there are two pair of variables. There is a pair of variable, correlation coefficient between them is actually 0. So the variables are uncorrelated. But are these variables really independent? A minute observation is showing us that no, they are not actually independent. These variables x and y, they are connected to one another. What is the connection? If you look at it carefully, you will find that I have represented the values of y as x squared. So minus 3 whole squared give you 9, minus 2 whole squared give you 4, and so on. So there is a sort of relationship between them, but correlation coefficient between them is 0. So rxy is 0 here, but y equal to x squared, and that is x and y are not independent. So here is a question may come to your mind that when we get that the correlation between the two variables is 0, what does it actually mean? What is the meaning of this quantity, of this particular statement? The meaning of this particular statement has been written below. When we find that the correlation between the two quantities is 0, it actually means that between the variables, there is no such linear relationship. I mean, the variables cannot be connected by the equation of the form y equal to ax plus b. But the variables may be connected to one another by a non-linear relationship. That is that happens when we get that the correlation coefficient between the two variable is 0. So correlation between the two variables 0 justifies the fact that between the variables there will not be any linear relationship, but non-linear relationship may exist between them. So remember, this is very important. I have underlined this particular section over here. So this particular point is very important. And if I plot the figure, you will find that since in this example, y and x are connected by the relation y equal to x squared. So if I plot the figure, this V-shaped curve is coming out, because you know this is the curve of y equal to x squared very well. Regarding correlation coefficient, zero correlation coefficient, I have to say another important point to you. Suppose we know that two variables, it is a quite obvious fact that if I give you two variables which are not connected, as we can feel, such as beauty and intelligence, we can immediately say that the variables are uncorrelated. The correlation between them is 0. Just like that, suppose I am giving you two variables. One variable is counting the mangoes on different branches of a tree, and another variable is counting the marks of student. These two absurd, this absurd pair, number of mangoes on a branch and number of marks by a student, this is an absurd pair, and you definitely know that the correlation between them is 0. But if I do not declare that what one variable is representing and the other variable is representing, then you'd never know that the first variable is actually representing the number of mangoes and the second variable is representing the number of marks. You can find some sort of correlation between them, but without actually knowing what they represent. Such a value, if obtained, is considered to be a garbage value. We are going to discuss further on this in the next session. I'm going to stop recording of this session.